I'm Jen Marlin. I'm the Executive Director of the Yale Center for Geospatial Solutions. Thank you for coming. Good afternoon. It's my great honor to introduce Adel Daoud, who's here with us. He is bringing a wealth of expertise and energy and insight to the intersection of computer science, environmental science, and social science. And it's that work at the sort of ecotone of these disciplines that really excited me about his work. I met him in Germany just a few months ago at a social science conference hosted by GESIS. I can't tell you what that stands for, but it was aimed at understanding how Earth observation data is used in social science. And so Adel's work really is addressing, in fact, it's really pushing frontiers in this area that kind of brings together foundational basic research with really important applied work addressing today's most pressing and complex problems like poverty and development around the world. So I was really excited because he was coming to the United States from Sweden, and he was going to the wrong university. We're not going to talk about that. I'll just say it's in Cambridge, but we were glad to have him come here. I won't hold that against you. So we're happy to have him here today and a little bit of tomorrow. And he's currently a senior associate professor at the Institute for Analytical Sociology at Linköping University in Sweden, with affiliations across leading institutions like Chalmers University of Technology, and Harvard. His work spans social science, AI, and global development, and his lab, the AI and Global Development Lab, exemplifies his commitment to interdisciplinary, collaborative research. So he's going to talk today about planetary causal inference, a field that he's really helping to define as it advances. And so with that, I'll stop talking and hand it over to Adel. Thank you.
Thank you so much, Jen, for that really nice introduction. It's great to be here. And can you hear me well? I think this is working well. Yeah. Is it too loud even? No. It's just that I'm hearing myself, so it becomes like interrupted, but I get used to it. It's such a fantastic view, and this is how I wish remote sensing would be, with this high definition of a view. No, it's fantastic. And we met end of November, so it was quite recent, and thought we will, great to connect. I'm glad that it worked out so quickly. So I'm going to talk today about this idea, planetary causal inference, and it's really more like an invitation to think about what would it mean to use remote sensing, Earth observations, particularly satellites, to think about cause and effect, and that's sort of what we in social science tend to think about a lot, and in environmental sciences likewise. So how can we leverage remote sensing, machine learning, domain expertise to further that intersection that Jen started off with? So what I'll be talking about today is sort of some selection of chapters that we are writing a book together with Connor Jerzak that is just now, hopefully this week, going out to review with Cambridge University Press, where we will be sort of visiting different domains in these application areas. So the book, I'm going to show you a little bit of that structure. I'd be very curious to hear your thoughts about how you would like it to be structured. Towards the end, I should say, I'll have a QR code where you can sign up for the newsletter. It's a way just keeping track and be able to sort of communicate to you in terms of the book updates, code base, data, and just your ideas. There's a forum there that you can write your ideas, and it's a way of keeping communication going. So this is taken from it's the contents of the book. So the way the book is structured, and it's really hard to think about, how do you bring together such a large field of expertise in Earth observation, but not only that, in computer science, which is moving so fast. The paper from 2023 can feel so old, that you can get a sense of how fast that field is moving. So how do you then, bring nonetheless in that expertise into a book that is meant to stand the test of time? So the way that we will be setting this up is in the form of ingredients and recipes. So it's basically a cookbook where the first part is set up in terms of going through the ingredients. So, one of the critical ingredients is Earth observation data. What is it? And I should just say, this is really sort of coming from introducing it to the social scientists. So many of you here, have worked with Earth observation data day one in undergrad school. So for you, this chapter would then be less relevant, but nonetheless, we'll hope that it will be relevant for you in terms of thinking about potentially, say, the causal inferential part, where you might not, have experienced that training as, say, an econometrician or economist would get. So the idea is to sort of compose together these ingredients, Earth observation data, measurement and sampling. Statistics is really important, as we talked over lunch, is that, we think about, this is, ultimately about understanding the world, right? And understanding the world, you can either collect all the data that the world gives you, which would be impossible, is so much data. So you have to sample, right? You sample because of necessity. And that's what statistics offer you, to think about measurement and sampling and uncertainty in your estimate. So hence there will be an ingredients about that. And then causality, obviously really important, is that once you have conducted your measures, about a couple of variables you care about, how do you think about cause and effect? Ideally, you should think about causality from day one, because you would quickly realize that you need to collect certain types of data to be able to conduct causal inferential conclusions. So then that will be another component, and then obviously machine learning, computer vision, that many of you have experience in. That field again moves super quick, but it's a way of introducing the basic components of how to think in terms of computer science. How would an algorithm see this data? How would you learn from that data in terms of the measurement setup? And lastly, which we don't talk so much about it. It's a sort of a little boring topic, perhaps, but hardware. Really, ultimately, it's you're going to be conditioned by what resources you have available to you in your university. Luckily, in Sweden, we have a national infrastructure for compute, so we can run big models, and the models that we run, the study that I'll be showing you from Africa, we run it for the whole continent of Africa. In a couple days, and that's reasonable. It's not a OLS model that you run in seconds, but it's still a reasonable training time. And so, how do you think about compute? How do you conceptualize it? It's not going to go over the whole computing infrastructure, but it's just giving you some heuristics to think about that, because a lot of the stuff that we want to answer will be conditioned, obviously, by what you could run ultimately. So these are the ingredients, and then thinking about the recipes. So the idea is that you would take parts of these elements of ingredients, and then you could then, I don't know how much of you have played Exploding Kittens, the board game? Yeah, okay. So no. Okay, so I mean, think about it as cooking. I think that's easier. That's the common denominator. So the idea here is that you have recipes for remote surveying. So the idea is like, it's sort of playing with words a little bit, remote sensing, but it's really surveying. That's how we think about it. It's a way of measuring through satellite imagery. And so we will have two chapters about that. One is about measuring the point estimates of interest, and that's what I'll be talking about in the mid part of this talk, of how you do that, and in a context like Africa, if you want to measure poverty, how do you do that? So that's chapter 8. And then 9 will be sort of doing the same thing, but from a different angle. How do you use segmentation models to think about, if you care about the parts of the image representing perhaps a forest or a urban area and so on. So how do you then deploy that? There are obviously many different other types of models that you could work with, but again, it's a recipe. So at the end, you'll see we'll be inviting you to think about your own recipes, and so it will be hopefully creating some kind of a momentum, a community about what we can share recipes amongst each other so that we can learn faster together. So then comes a part about the first, if you like, more causally inspired recipes, which we call recipes for planetary observational studies. So now you're not in an experimental setting, you have data that you haven't been able to control the treatment assignment, but nonetheless you might want to use some parts of the the measurements that you've done previously. So say that you've run, a recipe on AIDS, you've collected some measurements from poverty, say, and then you want to couple that with, how do you then couple it with existing econometrical methods of difference and difference? How do you propagate the uncertainty, perhaps, that you've estimated from the first stage into the second stage? So it will talk through some of these challenges, right? And another way to approach what images can provide is that, you might not be doing measurement at all, but you might say that I have some tabular statistical data, geotemporal, but there is some lack there that images can fill for me. Could be that the image, so for example, in the setting where I work a lot is that we think about the impact of World Bank development programs locally in Africa. Build hospitals, they build roads, they build water and sewage systems. What's the effect of that on poverty? So someone has looked at the map at some point in that location of the program, but we don't have access to those maps, and they might not exist in tabular format. So there might have been some important geographical feature that we miss in the tabular data. So then you could then arguably put forth an argument to say that we're going to use images to proxy that map, right? It could be going back a year, 10 years, 5 years, or the whole video stream, if you like, of a sequence of cell imagery to adjust for other unobserved confounding, so you can reduce the bias in your estimate. So that's sort of chapter 11. And then there are new techniques and relatively new techniques, I should say, synthetic control methods, that is sort of a mixture between difference and difference and matching approaches. And then lastly, but I would say almost as a methods developer as I am, and I'm sure many of you are, is that you would want to perhaps run some simulations to try out some ideas, right? You might want to generate images, satellite images preferably, that correspond to some kind of a causal system that you have in mind. But so how would you experiment with, say, generative models to create those systems, right? So how do you set it up? So we have a paper right now we're in the making to think about generative models and image space to proxy some parts of the causal system, the outcome, the treatments, perhaps confounding, and so you can then start reasoning about some kind of a signal-to-noise ratio. So that's chapter 13 here, and then recipes for planetary experiments. And here the idea is that you might be in a setting where you actually run an experiment and you say, what do I do with Earth observation data? And it turns out that we can give you at least the 5 ways that you could use Earth observation data to further a randomized control trial in the field. And so one of them is just to think about ways of block randomization. So block randomization, for those that don't know, is that if you have villages that you want to conduct an experiment on, you usually use tabular data to block randomize. You define these sort of principal strata in a way where you would start picking units within that strata to reduce the variance and make the sampling a little bit more easier to run. Usually tabular data, as I said, is the way that you use it. Could you use, we asked in this chapter, Earth observation data, image data, to further narrow down the blocking here of the units? Estimating effect heterogeneity, we have a paper that came out 2023, now an old paper in computer science, where you can look at heterogeneity, moderation, and image space. So you have you have the randomized, everything is fine in terms of confounding, but you want to nonetheless look at perhaps there is some geographical feature that is not in my data. Again, happened perhaps a decade ago or more, that would moderate the treatment effect. And so this chapter shows you how you could think about ways of deploying images to look at effect heterogeneity. Right? Auditing is basically, did the randomization work well? So you can look at, you meant to randomize in a particular way, but maybe there was a bias that slept in somehow in your randomization. And you can control for that by looking, at least within controlling, meaning within the Earth observation stage. Do the images basically look random enough to give you information that the randomization worked as properly defined? Transportability and generalizability basically means that you have run an experiment maybe in 100-something villages, but you want to know how that information would generalize to other parts of that country. And so the way that you normally do this is you use tabular data. But the way we were sort of playing around with an idea here is that you could use image data and conditional on images, you could then extrapolate to other regions of that country. Right? So again, it's conditional on what images gives you. So it might be not sufficient signal, but it's nonetheless a way that you could deploy it. Okay? And so evaluating long-term impact is basically you can say, we ran the experiment, but now we would want to follow up. So could we map the outcome of interest into the image space and then follow what happens with that outcome over time? So that's, roughly speaking, just to give you a taste of what the book will be about. And if there are any questions or thoughts, I'll stop here at 2-3 minutes, and please, reflect with me. Please.
Hi, thank you for this introduction, and I'm very interested in how could you handle any other intellectual property issues related with using that kind of data?
Intellectual property. So you mean if the satellites themselves are somehow protected, or you think about maybe some part of the survey being privacy protected, or?
Yeah, both are interested because I thought you use a lot of large-scale data sets. Mm-hmm. So I'm curious about how to handle the data privacy and intellectual property issues related with that data use.
Yeah. So we and the slides that I'll be coming into very soon, we use the demographic health survey. So there, a lot of the research that we're doing here is handling the demographic health survey. In your case, it might be something different, right? But in that particular case, there is a privacy protection mechanism already applied. And so we run with that protection on, so to say. So we never run into the issue of having to protect our own data, if you see what I mean. That, in fact, injects measurements error. So we'll be doing less good in what we could have done with that privacy protection off. In fact, the meeting yesterday was with the UN Stats is to think about ways of maybe collaborating so that we could run the models on their servers to be able to improve, or at least investigate how much privacy protection sort of erodes our estimates. Thank you. Any other thoughts or reflections on the book? Something that you think it misses, or you would really want to see, but it's not there?
About counterfactual images.
Yeah. Oh, you mean the generation stuff there?
Counterfactual images.
Yeah, kind of. So basically, it's really interesting, the kind of factual stuff. So you could think about the way that we think about these generation of images is that we don't necessarily think about them as kind of factual images. They could be under certain assumptions. I think kind of factual analysis is really interesting in a sort of Pearlian sense, the Judea-Pearl work. But you need to have very specific causal structure to be able to make kind of factual statements about the world. The way that we're thinking about the image generation is basically a sort of a simulation setup where you could try out different causal setups. And I give you one example. So imagine that you have an idea that in the image there should be, the outcome should affect, I don't know if there are any whiteboards I could use. Well, okay, here we go. So how many causal graphs? Yes, a bit of a familiarity. So imagine that you have a treatment here. I don't know if you can see it there in the back, but basically you have a treatment and then you have some kind of an outcome. There might be some confounding here, and these are say measured in tabular world, and then you have an image, right? So the idea is that the outcome should imprint itself causally into the image. So what does that mean? Well, it basically means that whatever the satellite captures should be informed at least by how the ground truth looks like, right? So this could be poverty, this could be a development project, this could be, it could be a resource where the project is basically located, so it's co-located. There's a bias of where they locate. So what I mean by generating images is that you would never see this causal structure in the real world, right? So you can't really, you just assumption. What you could do if you had a simulation system that generates these tabular data and generates this image, you can now start playing around with how much signal must Y imprint into M to figure out ways of training a model F that takes M and then predicts Y hat with a certain level of accuracy. Okay, so this gives you a leverage to make an argument that my approach of how I deployed at least under these assumptions is informative, right? Otherwise, you have to always empirically start showing it. You basically have to do the work and then defend it. This gives you like a way of trying out some ideas and before you deploy the full work, okay? And then you could have this as in an appendix. And if you're in methods development, you really care about how the system how the system is generated, because you want to study the behavior of the algorithm under some, nonlinearities or some hidden confounding or whatnot. So that's what this paper is about. So it's not about kind of factual image generation as such.
So can one perceive as X and M or exogenous Y is exogenous and T is some policy instrument?
Yeah, you could. Yeah, you could. I mean, the idea is that you could make many different types of assumptions. You might say, actually, what if we have the image is not only imprinting from what happens on the ground, but also, the location of the project, how it manifests, is also imprinting into the image, right? So basically saying you can see poverty, but you can also see maybe road construction, right? And if they couple together, how would my algorithm react to the system? If I'm actually only interested in measuring Y, but T is in there too. How do I separate out information about T? Because I don't want T in the image. I really want only Y, okay? Because you might want to separate out the measurement step. And this is basically information leakage problems in certain setups. So you want to then be able to study this behavior under certain assumptions. Okay? So that's sort of the idea. Gives you more leverage, more tools. Okay? Any other thoughts before I move on? All right, cool. So let's get into the meat of the problem, but actually before that, I want to mention a sister project that we're working in. It's another book, but it's a more slow-moving process. It's called the Trinity of Statistical Learning. It's with my stats colleagues, Professor Xiaoli Meng, James Bailey, and Kyla Chesalov at Stats, all three of them, where it's basically coming from this project that we're leading. But we're thinking more about statistics in this new age, right? Of where you use Earth observations, you use other types of modalities where you're faced with, multi-resolution, multi-phase, and multi-source problems. Essentially that, you have multiple sources that you're working with. Statistics is basically in the old age, if you might. Sorry, perhaps statisticians in the audience. I see myself intellectually as statistical, but basically you think about a population that you're interested in. You want to design your sampling strategy. You go out and sample, you collect data, and you have a tabular nice format, and then you deduce some parameter of interest. And obviously we know that we're not in that age anymore, and so how do we adapt statistical inference or learning in general when we are dealing with multiple sources, multiple phases? Basically, people are doing different things in different steps, right? So I might measure Y here. I give you this Y hat, and you might do something else with it. But you don't know, what choices I made, what uncertainty went into this. And so how do we then create a science in multiple steps that are able to encode that uncertainty throughout the steps, right? That's sort of what the multi-phase idea is. And so that's hence what it's called a trinity. It's basically these three things that sort of comes back at us. So it's based on a joint course that we are running, and that's actually the course I'll be going to present in this unnamed university next week. So if you want to join virtually as an auditor, just send me an email. I think we can definitely sign you up. It runs Tuesdays 9 to 11:45 Eastern time up to April. All right, so that's that. Let's get into remote measurement. Okay, so I'm particularly excited about this part of the project because it sort of is very tangible, right? I really love the causality stuff, but I tend to start with this just because it's the most tangible way that we can think about how we can couple Earth observation, EO here, and machine learning, ML methods to think about large-scale measurement problems, particularly in environment and social science. Okay, so if we start from where global development is, basically sustainable development, broadly speaking, is that we know that humanity has made large strides towards developing the living conditions of humans on this planet. But we also know that there's huge amounts of inequality in terms of the various dimensions of living conditions that people require to live a decent life. Okay, so if we think about the dimension of drinking water here, we have different levels, right? So in the Western world, in the industrialized world, we are used to just going to the tap. There's a water fountain here. I can just fill it up, and I'm all good. In other places, you have to walk up to 30 minutes, maybe hours to acquire, a safe well to gather water from. And the same goes for many other types of dimensions. So the question is, how do we think about the distribution of humanity at the planetary scale, and what pushes the living conditions up, one step or multiple steps, this ladder? And obviously, there's this trade-off of environmental aspects that I'm not going to talk about in this talk particularly, but that is sort of another really important dimension in this problem. In this particular setup, what you need to understand the determinants of what drives development is obviously a lot of data, a lot of outcomes, what we call Y, right? And however you define these Ys, health, education, living standards, and what indicators you use, you would need a lot of data. And in the data scarce places, like in Africa, we just don't have sufficient amount of geotemporal data to really study what is going on the ground. So what we are doing, at the AI Global Development Lab is sort of pursuing this vision of combining AI, Earth observation, and social sciences to analyze the causes and consequences of global development in a historical and a geospatial world. So just to give you a sense, many of you work in Earth observation, so I don't really need to convince you, but if you look at, one particular town, say Cape Town, South Africa, we start 1984, and we look at the visual patterns of what is happening in this city. We see the structured information for the human eye visually that there is definitely signal in the Earth observation data, right? Just qualitatively looking at this, you see the development of roads, neighborhoods, and so on and so forth. So, this is Landsat, right? So it's 30 meter square. You don't see humans walking, you don't see bicycles, you don't see cars. There are limits to what this data can give you, but there's definitely signal there. And the question, the hypothesis that we are asking is that how well can we measure health and living conditions? And how do we do that? Well, you need training data, these blue points, right? And you need satellites to sort of capture this information. So we have these blue points where we can train our algorithms. And then the idea is to extrapolate, interpolate. So we want to create these heat maps to the right. But we also, not only do we want to do this spatially, we want to do this temporally, right? So we want to then, the idea here is to train on the blue points, again, temporally and spatially, and then extrapolate to this red point. And once we can do that, we can then say, in this particular region, the poverty estimate has increased or decreased with this certain amount. Okay, so that's the intuition for what we are going to do. And just to hammer in the importance of time, why time is so important. If we take Cairo, for example, here in Egypt, you can see that if you would only look at the still image, as cross-section, you don't really capture what is going on here in the left corner, which is that if you look at 1984, there's basically nothing there 30 years ago. But then this neighborhood emerges from basically nowhere. Okay, so that's what time really gives us, and that's I don't have to convince you, but I really want to say that this is why temporality and spatiality together is critical. And so once you have trained an algorithm F, so we call this F just in general. It could be any type of computer vision model. But what we want to do is that we, for example, in the case of Burundi, where there are no surveys, we can at least give it satellite images. And when we give it images, we are hoping that, again, the hypothesis is that we can generate these heat maps with a certain level of accuracy. And if we look at the case of Burundi, again, we're doing this for the whole continent, but just to hammer in one particular case is that if you look at Burundi, you see that there are 2 surveys in Burundi, 10 and 17. And so if you would do any kind of causal analysis, you'll be stuck with these. And the stuckness is even worse in the sense of that these are repeated cross-sections. You don't know which households are actually, doing what, right? So it's just basically 2 surveys that you have. But with our data product, you can now really, get at this space and time part that is really critical to any type of explanatory science. Okay, so the data that we are using or will be using in this analysis is Landsat, and as many of you know, there are different Landsat products. In our case, we start with Landsat 5, and we'll be starting in the 90s. And we started in the 90s mainly because that's where we have training data. So DHS training data started in the early to 1990s, yes. So Landsat 5 will be combining it with some Landsat 7 as well. And obviously we want to avoid the scan line failure correction problem in Landsat 7. It turns out that even if you run it on Landsat 7 with these line failures, you'll do okay. Okay, but we want to minimize noise. So what I'm going to show you here is really sort of the results that was published in this AI conference, the International Joint Conference for Artificial Intelligence, the special track on AI for social good. And the DHS data that we're using is from 36 countries, as I said, from the beginning of 1990s up to 2019. Where we have about 60,000 primary sampling units. So again, these are, I don't know how many of you worked with the DHS, just by the show of hands. Yeah, okay, so this is a fairly unfamiliar data set. But essentially this data set is commissioned by US aid. So every country that receives aid from the US, but not for very long, given that we have a new administration. The DHS will be decommissioned perhaps as well. But the DHS, for that relationship, they have required for a long time that every country would undergo this sampling. It's a way of monitoring how well US aid money is being used. But the nice thing with these surveys is that for about 30% of them, they come with GIS coordinates. So you can take the household survey. These surveys are pretty extensive, so they would, there's a surveying agent going and knocking on doors and have a surveying template, and they would, ask you, do you have a television, can I come in and see how, what kind of housing quality you have, and, they would collect a lot of asset information, and so that's what we're working with here. And what you're seeing on the map is the distribution of those primary sampling units, and they are each sampling unit, each point is a aggregate of about 20 or 30 households of this international wealth index and material assets, which I will be showing you in one slide here exactly what that contains. Okay, so that's the training data, and the outcome itself, the ground truth, just to unpack that a little bit more. So what is this wealth index? So this wealth index is composed of several indicators. These are the indicators that are in this index. And so what you do with this is that you have the slew of these household responses, and then you run a PCA model on top of it to reduce it down to a sort of a one-dimensional measure to make it easier to handle. And so that's what the International Wealth Index is it basically takes the PCA measure of the whole sample, and then you have a one-dimensional measure that ranges from 0 to 100, where 0 is the absolute poorest, 100 is the richest, but as I tend to say, it's not Bill Gates rich. It's really sort of upper middle class richness. So what does it mean to be on the scale numerically speaking? So if you take the responses, you go to a household and you get these exact responses that you have, and with a television you get a 12.73 index. So you'll be here somewhere in the poverty distribution. If you remove television, you'll be bumped down to about 4. Okay, so just to give you an intuition for what happens in this quite abstract index in terms of numerical values, but as you see, it contains very sort of concrete descriptions of the household. Okay, so the satellite image data, we take the full available bands, including we add the nightlight band, and we do that for the reason of that we know that nightlight data in development economics have been shown over and over again to be an important indicator of what happens on the ground. So this alone, if you would run this approach of just using this nightlight information, and you predict it in the same way that you would predict it as if you had the whole slew of information, you get a prediction rate of 0.5-ish in R squared, and the rest will come from these multispectral bands. Okay, and we're using, I should say, the median of cloud 3 pixels, and we are aggregating the 3-year image temporal window. So this aggregation I'm not fully happy with, because it's sort of a 3-year reduction of the temporal variation. But nonetheless, we sort of replicate. It was based on replicating another study done by colleagues at Stanford, and so we wanted to follow their procedure more precisely in order to benchmark our model against theirs. But we are working on an improved version where it's a 1-year aggregation, or potentially even no aggregation at all, but using the full available imagery within the year, which is, or at least a sample of it. Roughly speaking, 26 images per point that you would have because of the bi-weekly visiting time of Landsat. Okay, so and then we have for each DHS point, we have the full history of their imagery. So we have a sample of a DHS, say from 2010. You have one outcome. So remember, it's only a repeated cross-section. For that point, you only have one point, and it will exist here, but the image space, it gives you the full temporality. So for every point, if you imagine the data set, is that you have this IWI outcome, but you have also the full image history of that point. Okay, so it's sort of a little bit of disjunctness between the measurement of the survey and the image space. But again, the idea is to give the model as much of the image history that it has, so it can learn as much as possible from these images. That's the intuition, and so that's why we use that setup. The benchmark, and again, this refers to another paper done by colleagues at Stanford, the Jay et al. 2020 paper, which uses what we call like a single frame model. Basically, it doesn't look at the history of images. It doesn't have a temporal awareness, if you like, this algorithm. It basically takes all the images and all the data points and sort of disregards time, if you like, and then just trains it on that data set. What we do in the innovation, the algorithmic innovation, in this particular study, is that we add a temporal awareness. We basically repeat the single frame 10 times because 10 times 3, you get 30. And the idea in the upcoming paper is to do it, you have 30 of these models, and they connected through a recurrent layer here, a layer that enables the algorithm or the algorithms, if you like, to speak to each other in terms of what is going on temporally here. Okay. So, and we're using a way that we connect this, and this is basically almost like a Lego brick. You can change it for different types of way of connecting the information. The one that we used is called LSTM, long short-term memory algorithm. Now you would use a transformer, which has proven to be very powerful in large language models and beyond. Okay. Any questions or thoughts at this stage? Please do interrupt me if you have questions. Yes.
How much are the metrics you're using for poverty like, is that just based on what's most available, or is it based? Do you think, like, are you considering what is like a good, generally like culturally relative metric for well-being?
Yes. So we are using the. I mean, in a way, we're not even using a definition of poverty. In a way, we basically just using this wealth index that is used in the demographic health survey, and it's a metric that is used within the UN and within the policy sort of area of this. If you want to, the way that we sort of transition by thinking from that measure being a health and living condition measure to being poverty is that we think about where in the distribution you are in that metric. And we think about the lower, 10, 20% being the poorest. So if you're there, you'll be defined as poor because that will correlate highly with certain child health outcomes that are very detrimental for children. So the one unfortunate thing in the DHS that there's no income measure, so you can't really easily translate to the $2 a day metric that the World Bank use. But again, this comes from also a tradition of poverty measurement that thinks about deprivation, more of a deprivation approach, meaning that what do people actually have access to rather than how much do they have in their wallets, right? Which doesn't really translate always to books and television and student housing. Yeah, please.
I heard you mention the number 30. I wonder what is special about 30.
30? You mean the 30 years?
Oh, 30 years.
30 years.
Okay.
Yes, 30 years, exactly. Yeah. So and that's after an explorative data analysis, like how does the DHS basically outcome, what's the distribution of that? That starts in the 90s. And so basically that gives you 30 years of data to train on. Yeah, that's the idea. Please.
My apologies because I arrived late, so maybe you covered that, but I'm interested to learn a little bit of the infrastructure you have in your lab in terms of how much computing power, how many team members, maybe for one project if you have too many, but just curious about the scale and how do you manage data?
Yeah, thank you. So I'll be at my very last slides. We'll be showing you the lab face on. It's really not a one-man show at all here. So I'm just representing the team. But we are just to answer that question, we're about 10 individuals roughly speaking, give and take depending on how many master students comes in during what time and so on. And we're it's sort of a hybrid lab where we're scattered. In Linköping University, Chalmers, so Linköping is the social scientists mainly, the computer scientists at Chalmers University, and then the statisticians at Harvard, and now one of our colleagues moved to University of Texas, so he's leading the causal inferential development at University of Texas there. So yeah, if you're interested in collaborating, always happy to talk. In terms of compute, we use the Swedish National Infrastructure for Computing. So they have sort of an internal application process where, these computers are, basically NVIDIA cards throughout. There's a list of different cards that you could use, and you can just surf in now and look at what there are. And we use what is available at that time to make our waiting time less. So this obviously, when it's public, you have to wait. If you have your own, it's costly, but you can run more. But yeah, I think at that time we ran with the H100 cards, I believe. I'm a little unsure actually exactly. I've been jumping a little bit depending on availability, but that's yeah.
Is there a way to ensure the variation of satellite data, like a map of like a certain relationship to the distribution of the property?
Mm-hmm.
So, just curious, maybe the satellite data does not have enough information to capture the stream property.
Yeah, so I'll show you in a minute about exactly that. So maybe we can continue based on that question. So you'll see there, what you will see is essentially where our approach is doing better and worse based on the ground truth data, on held out data.
And the second question is about the absolute property versus the relative property.
Mm-hmm.
Like the property standards may change over time.
Yes. So it's a great question. So this is where you could definitely develop whatever metric you want to use. You can think about ways of adapting that for this setting. This you should perceive as sort of a an example of if you would use the IWI as a metric for your poverty, how well you can measure that. Now, to pin it to also the underlying question about income as well, there are early studies that use the LSMS, it's the World Bank surveying facilities. They have income, and so they estimated, how well can you actually deploy this to measure income, and it turned out that the results were less interesting than you will see here, less impressive. But we don't know, if those results are because there were too little data to train on, they were trained long enough, or it was something else, if it's a signal problem, because the LSMS is much less, there are much fewer surveys to run on. Yeah. So, the limits of this approach is sort of yet to be determined. I think that's sort of almost the holy grail right now in this field. So let's talk about the results. So sort of pin it to your question more exactly. So what you're seeing here are basically 3 buckets of how we set up the training. So for some reason my highlighter is not working. It could be that I have to open up that software. We'll just leave it at that. So what you're seeing here are 3 buckets of results. These 3 buckets represent the way the algorithm was trained, the way that we created the test training split. Okay, so let me just walk you through these, and then you see within them you have different algorithms, basically different standards or different ways of handling the data. So the easiest to understand is out of country. So you have basically Africa, and then you split based on countries as clusters. So every DHS points, you have Africa as a square, and then you have countries. You have DHS points. The way that out of country works is that it looks at countries as units that you think about test splitting, right? So you take out 30 something countries, you test on 6. Then you redo that cross validation style, and then you get these results on out of country. Out of time span is basically thinking about time. So you have another layer here, another layer of time, more DHS points. And the way you split it is now just basically time splitting. And then out of area is basically just thinking about ignoring countries, actually looking at time, but looking at the basically if you like a cone that goes through time and space, where you look at, so areas cannot overlap with each other, and so you would basically use an algorithm to find ways of like which are the least or most overlapping areas with each other, and you create the test split. This is important because the way that you train the algorithm, because we know that there's a lot of geographical and temporal overlap, right? And for these machine learning models, the key here is to think about IID samples, right? They should be independent, but we know that time and space makes them dependent. But still, like we have no clear sort of a silver bullet for how to solve this dependence in terms of training. So this is what we do, and what you see is that however you do this in terms of the 10 frame. So the 10 frame model basically uses the whole history of images to make this prediction. The 5 frame model takes from this 10 a random sample of 5 to predict these outcomes, and it's just a way of saying how much information does history actually provide. And throughout you see that the 5 and the 10 frame are pretty close to each other, but the 10 frame throughout outperforms the rest. And if you just meditate over these results, 0.75 for the time span, out of time span, they're basically 0.73-ish, say, on average, and R squared. So this is the whole sample. You take the test sample, on that whole thing, you calculate the R squared. If you meditate on this and you think about 0.73, that's, 1 is perfect. 0 is basically sample average, right? It's actually quite amazing results, right? If you take any social science study and you want to run a regression with tabular data, the best you can hope for if you're obsessed with R squared is some sort like 0.25, 3 something, maybe 4, if you have highly dependent data, maybe 0.6 at best, I don't know. But these are quite amazing results. So you have to now, what we do here in the following slides, is to probe these results a little bit more critically. Like we ask, okay, so the sample average is pretty high, that's great, but where are we doing best or worse in terms of error? Okay, so in terms of R squared again, sorry, but we'll be looking at the error structure right after these. So you see that the R squared after 2000s is better overall. So it's basically averaging on that 0.7-ish R squared, but pre 1990 we get a 0.4, 0.6 R squared, and that's partially, due to that we have fewer training samples, but partially also because Landsat and during that period there's a lot of missingness, and partially because of a privatization program that the Landsat went through. So a lot of images were not retained, so we end up with black images. So that's the temporality. If you look at the by country prediction, so now we look at the, we aggregate to the country level and see how well are we doing within countries. You see that countries that, like South Africa and Egypt, we're doing actually worse on than the rest. When we get a prediction about 0.3 R squared. And do you have any hypothesis for why that might be the case? It turns out that Egypt actually is the country that has most surveys, and it's about 7 surveys, DHS surveys, and it's a country that actually receives a lot of aid from the U.S. Yeah, so it's actually because of the Nile, the population density. So most people, both rich and poor, live in a very dense, close area. So the satellites, when they take an image, they can't really discern, rich and poor, because the image looks basically the same. So that's, a working hypothesis of what's going on in Egypt, for example. So you really need, separation. So this calls also for why thinking about the image size is also so important, especially in dense areas. And thinking about the predicted wealth to the observed wealth, we can start asking a little bit the question that you raised of where are we doing better? And we see that those IWI outcomes is basically, in terms of the error, is a little bit harder in certain regions up here, actually. This is where we do a little better in the mid and the tails. And that's because I think our hypothesis here is again separability. It's easier in a rural area to see exactly what's going on where you have this pinning of imagery. Okay, so I have about 7 minutes left, so I think I'll speed up a little bit. But to continue the probing, but now we're looking at this from a qualitative perspective, we basically take the points that have the highest error. Okay, so we're looking at their residuals, and then we look at their image history. And we see that these points are actually points where not much is happening. It's really no villages, no nothing. And this is most likely due to the privacy mechanism, that these points have been, cast out about 5 kilometers at maximum, and they might end up in a desert or in a mountain. And so then the signal to noise ratio really is distorted. The areas where we see most improvement are places like these, Morocco, Namibia, where we clearly see there are, human settlements, and there is, a lot of activity on the ground that the signal to noise ratio is much higher. Okay, so this is sort of confirming our hypothesis of centering and image size and whatnot. That is critical. All right. So if you now validate this, you aggregate to the country level, you take these estimates, you look at the Human Development Index, you see, a pretty good correspondence, not perfect, with the Human Development Index conducted by the UN. This is just a validation exercise to see, how well is it matching up. Okay? So now you're done. You have your algorithm. You trust it, with some caveats here and there, caveats. So what you do then is you extrapolate. You do like inference now. You basically have an algorithm, but you have all these images that are sitting there where you haven't trained the algorithm that you can generalize to. So you basically take the algorithm, you take all the images, from the 1990s up to date, and then you get these predictions, you get these white hats. And we do this where there are human settlements, so we're using human settlement maps as cookie cutters to basically segment so that we don't predict in areas where no people live. And so what we do here as well with these is that now you have your data set, this temporal, you can do some simple exercises, and what we do here to the right in this image is that you see we basically forecast which of these communities will reach most likely the SDG goals of no poverty. Basically setting the threshold at the lowest quantile, we ask which one will reach above that lowest level. And the red points are the points that will not reach the SDGs given their trajectory that we see temporally speaking. Okay, so these are the areas where, from a UN or policy perspective, either way you need intervention. You need to intervene to speed up growth. And so, yeah, this becomes a policy tool to figure out what to do. But next step is to figure out the causal effect side, right? So where do you intervene? You can take these estimates and also recalibrate them to get a population or a continent-wide population estimate of what these red points mean. It's about 142 million people not reaching the SDGs by 2030. Okay, so more work on this will be coming hopefully by before the summer, and we're also very interested to hear how if you find these data interesting, working with them in various forms. What will be coming up soon is that we'll do more outcomes. We'll do this aggregated version of this data. We'll do better temporal resolution, as I mentioned. Also, spatial resolution is very important here, so we'll be improving that as well. And also uncertainty quantification, which is a very important part of how uncertain is the model about these predictions, so that you don't get lured by just having a point estimate. Right? So we have sort of a similarly inspired paper in India that is doing the same exercise, but here the problem is more, how do you work with incompatible surveys? So the DHS was nice because, it's the same survey through time, everything is harmonized. But here is how do you think about if you have a census and the DHS, and then you want to do something similar, how can you conceptualize this problem? So if you're interested, take a look at that. There, I won't be talking much about this paper here. And as last time I presented, Jen, I had the causal part hanging, and it's only about 2 minutes left of this talk. But yes, maybe I'll. Maybe, what do you say, Jen? Shall I stop here or do a speed?
Keep going. If people have to leave, they're going.
Yes. Okay. I'll keep going just to show you. Yes. So I wanted to take a couple of step backs, and you think about the book again. So you saw one recipe essentially. That was one recipe of doing remote measurements, and so that would be that chapter. But you think about the other chapters of the causal part, which is getting at it from a explanatory perspective. And so here we have a couple of papers doing exactly this. We have developed a R package that helps you run some of these causal experiments. So take that for a spin. What we are hoping, and Jen, this might be a thing we can do maybe next year or towards the end of the year, is that we can come up and do a workshop on some of this code base. That would be a way of doing more an interactive test of how this is working, but also what you find interesting and how we can adapt this material to your interest. This was a last minute slides for Luke, who's not here. Fortunately, I think he had to stay home for family reasons. But some work that we're working on with him and others, just to highlight some of the collaborations also between the lab and Yale already, is to think about, how do you think about geographical regression discontinuity design, improving that with the help of EO data. So the intuition here is really, you have, I don't know how many of you know regression discontinuity design?
Megan is working on it.
Okay, cool. All right, very good. So then you sort of understand the intuition is that the idea here is that you look at the border. Border is sort of the important running variable, and oftentimes you probe this only using tabular data. The idea here again is that could you add Earth observation data validate, is this border relevant, at least if you look at it from the image space. So it adds another control. This is what this paper is about. Quickly and rapidly, I give you an intuition for, say that you ran that recipe of measurements, and now you want to use it for something like evaluating the World Bank and Chinese impact. But not only that, you want to also use images to add to the adjustment set, right? So again, you remember this unobserved confounding that might be lurking in these maps where Chinese development officials might say, yeah, we want to locate here, but not there. And they have a map, but we don't have access to it. So can images proxy these maps? That's sort of the intuition behind that. So you're doing two things, two recipes are playing out here simultaneously. And so the setup, very quickly, you have these development programs, they're geographically located. So if you look at the website of adata.org, they have all these data openly available you can work with. And so what we're doing, just to give you a very quick intuition about this equation, is that you basically estimate the propensity model, this probability of a treatment, D, the probability of where Chinese program will be located, conditioned not only on tabular data X, but also on image data of that unit. Okay, so it's quite simple, but it's still complicated because this image space is very large. And how do you make sure to retain signal in this image? Do you just concatenate the pixels? Do you run an embedding on this image? Do you run a CNN? Do you run a transfer? Depending on the modeling structure, you might enhance or destroy the signal and the information. So this is where you have to sort of think about this F again, is that is the way the image enters the equation and how that influences your analysis. And if you're unsure, the idea is that you could then perhaps run a simulation first and figure out how much signal must I have to before I can sort of confidently run with this. Okay, so this is just a variable setup, and this is the geographical distribution of these treatments. And here I'm just showing you an example of health projects. So there are multiple types of projects that the World Bank and Chinese programs run, but these are the setups of the health programs, and so you might then ask, okay, so what are the interesting results? What are we going? Well, so these are the main results of what you would, if you would break down World Bank, which are blue, and Chinese programs, which are red, by sector, which are these categories that you see here on the left. So what the overall impression, which is interesting, and I should just say that the y-axis here is depicting the causal estimate, the causal effect estimate. And it's in the IWI scale. So if we're going to walk through, for example, the health program, which is up in the second row, you see that a Chinese program overall is doing better than a World Bank program in terms of IWI impact, and that effect is about 15-ish IWI points. So when there's a program, on average, the idea is that they will affect IWI by 15 points. I showed these results to our Göttingen, University of Göttingen Development Economics colleagues that actually developed this Chinese program data.